Hello again. So what we're going to talk about now is another type of binding, which is address binding. So address binding. So the idea here is instead of type binding, is we're answering the question, when does the memory cell when is the variables memory cell bound and unbound? I ran out of room there. Unbound, there's my D. Okay, so if we can answer that question for particular types of variables in a language, then we'll understand how variables in memory are used in that language, which is very important for understanding how to use a language. Some languages provide a wide variety of choices in terms of when this binding and unbinding occurs. And other languages really don't provide any choice. They may just have one way of doing a binding and unbinding. So I'm going to be talking about this in a lot of detail, and I think it's worthwhile for you to have sort of a big picture before we start down the rabbit hole. So there's several flavors of these address bindings, and they are static, stack dynamic, explicit heap dynamic, and implicit heap dynamic. Okay, so we're going to just knock these off one after the other, and we'll start off with static. And for many of you, the idea of static might seem a little strange because you've actually never experienced it. I mean, I know that there's a static data type in Java, or a static keyword that you can place in Java. So I'm going to have to do a little bit of research on that before I come down hard on whether it's really truly static the way I'm going to be talking about or not. So leave that alone for right now. So when we talk about static address binding, what we're saying is that the memory cell is bound to a variable at load time. All right. Now, if you might be saying to yourself, load time, what the heck is that? I guess it's worth taking a moment to just remind you about the general process that you go through when you're writing a program and then executing it, right? So you're in an editor, then you compile your code. If your code uses libraries, there's a process that's going to link your code to the code you've written to libraries or code that other developers have written. The code's going to then get loaded into memory, get ready to execute, and then it's going to execute. So that's the process that gets followed for pretty much any kind of program. Even Java follows this to some degree. I think with Java we take a couple shortcuts when we do compiling. We compile it into intermediate code. The process of linking can occur there, or I guess it can occur as the code gets loaded into the virtual machine. The process of loading takes the intermediate code and loads it into a virtual machine, and then it's executed in the virtual machine. If you're dealing with something like a programming language like C++, what happens is that you edit the code, you compile the code, and it produces something called an object file. The object files are linked together to perform to create an executable. The executable is then loaded into the computer's memory, and then it's executed. So again, we're following this edit, compile, link, load, execute process. So one of the things that's true about static address binding is that not only is the memory cell bound at load time, but I guess we can say in parallel, the memory cell is unbound at the termination of the program. So it doesn't happen before then. So if you've got a static address binding, that memory cell is going to stay allocated for the length of the program. So where might you find a use for this type of address binding, static address binding? Well, here's a really great example from something like C++. Before any of the methods that you write in the code, you can just declare variables. So for example, I might have a variable called Boolean. Let's see, in C++, it's a bool. So bool debug equals true. Now, the thing about this particular static variable debug, and then I've got some code in here. Something I might have like an int main void, and then some code, and I might have some other methods in the file that contains this program. The thing about this variable, this debug variable, is that it's globally accessible. It's actually called a global variable. And that means that this method here can access debug, and pretty much every method can access debug. And if you link other modules to this main program with a little bit of syntactic sugar, those methods can also access this global variable. So it's pretty wild. I mean, it's very different from the way you program in something like in Java, where you might have a static member of a method, but it's really only accessible to that users of that particular a sort of static member of a class is really only accessible to users of that class. But here what we're talking about is a single variable, and if it's made static outside any method, every method in the entire program can access this variable. So that's really useful for something like debug. Every method may want to know, is debug on? If so, there's some debug output that I'm going to provide. So that's a little sidetrack, though, because we're not really talking about scope right now, and a global variable like debug has scope. But it is showing you how global variables can be very useful. Now, clearly, this type of variable, it doesn't make any sense for this variable to have its memory bound at runtime, because every method in the entire program should be able to access this variable. So you need to have the variable and the memory associated with the variable allocated before you start running code. So that's why it has to happen at load time. So it's kind of a long-winded explanation, but it got me to the point that I wanted to make, that sometimes static variables are really useful, like this debug variable, and they need to be pre-allocated before the program is actually executed. Okay. So that's a case for it. Now there's a case against it as well. One of the problems with statically allocated variables, since they can't be unbound until they're terminated, is that you can't. So I guess let me just say this. So this was the good stuff. This is a good example of why you might want to do this. And here's a bad example. You can't recycle storage. So if I wrote some code that looked like this, and this is something you could do in C++, I could say int array, 100,000. And, then I could have my main program. So this is kind of awesome from one respect, right? I've got this huge array, maybe I'm using it to store lots of data or something like that, and it's pre-allocated for me at load time. So the moment the program's loaded, the array is good to go. I don't have to pay any performance overhead for allocating the array later in the program. So that kind of rocks. The thing that doesn't rock, though, is if I get to a point where I don't need the array anymore, there's no way for me to get rid of it. The space for the array is already taken up, and it's going to be there until the program ends. Now, that can be good and bad. I mean, so the bad part is it stays around until it ends. The good part is what I just said. It's pre-allocated. If there are a lot of methods that I have that need to use some large array and work with the array, and it doesn't even really matter if the methods need to share the data in the array. They just need some giant scratch space. This giant global array is available. Another problem with the bad, though, if this giant global array is available and lots of methods can use it, is there's an issue of managing ownership of the static data. If the static data also has global scope, it's not clear who owns that data. And if you were the one who originally created this global array and you plan to use it in just your methods, and someone else linked their program code to your program code and said, oh, wow, there's this giant array here. I could use that for stuff. And they started using it. Well, that may not be such a good thing. And they may want to use it for the same reasons that you use it. It's a big array. It takes up a lot of space. It's pre-allocated at load time. So, why don't I take advantage of it at execution time? So that can be another disadvantage to using static data. Okay, so that takes care of the first type of address binding, the static address binding. So the next thing I want to talk about is stack dynamic address binding. I'm fiddling around with case here. I'm using the iPad to do a lot of this writing, and I'm not sure I like it that much because I don't have as much white space to write on as I do with some other tablet devices I've used in the past. So anyway, I keep messing around with, do I write these topics in all uppercase or do it in stagger case, and I don't know. I haven't made my mind up yet. All right. So here, what's going on is the storage is dynamically bound. So it's first of all, so memory is bound and unbound using stack memory. So you might be saying to yourself, okay, stack memory, what the heck is that? So I'm going to draw a picture for you of what a typical program looks like when it's executing. All right, you can imagine that this is memory associated with a typical program. So you can imagine memory's got to be carved up into a couple of different parts. All right, so one part is for static data. Now, not all programs are going to have this, but some programs do have this. They have static data. Another part is for code. Those are the instructions that are executing in your program. So code is never going to change. I don't need to draw an arrow there. Code is never going to change. The memory chunk associated with static data and the memory cells that are bound to variables that are static data, that is never going to change. The values inside that static data can change. That's quite possible. Right? That debug value could change from true to false in the example I just gave. But the memory cell that the debug variable is bound to, that's never going to change. That's fixed at the moment you load the program. And then there's two other chunks of memory. One is called the stack, and the other is called the heap. And they grow towards each other. So the heap grows down towards the stack grows up towards the heap, and they serve different purposes. So right now I'm talking about stack dynamic address binding. So I'm going to show you what happens and where that happens. And this actually happens in Java, as well as many other different languages. So if I have a method, let's say, like let's call it int I don't know, int f. All right, and then inside f, I say int x equals 42, int y equals 10, and then I do a system out print line of x plus y, and then I leave my method f. Okay. Oh, I need to add a little more stuff here. Maybe I say public static. Oh, I'll make this a void. I don't want to make this an int. All right. So public static void f. All right. So it's kind of a useless little function, but it does illustrate a point. These two variables, x and y, their types are bound at compile time. We're going to, well, actually, their types aren't bound at compile time because they're going to be bound at runtime. But there will be some type checking that's done at compile time by the compiler, though. But when this function f gets executed and the variable x pops into existence, so x is going to pop into existence at runtime, it's going to be assigned a type of integer, and it's going to have an initial value of 42. Well, the memory cell that's associated with x is going to be carved out on the stack. So here's x, 42, and here's y, 10. And once we do the system out print line of x and y, and we're done executing this method, and the method ends, the memory cell that's associated with x and the memory cell that's associated with y are both going to go away. So they're created dynamically on the stack, assigned values, used for the duration of the method. When the method's done executing and the method returns to the caller, there's some cleanup work that the program does to get rid of x and y, and they're basically deleted from the stack. So as you can imagine, methods getting executed, one method gets executed, then another one gets executed, and another one gets executed. And each time a method gets executed, variables local variables are created and bound to memory cells on the stack. And then when you exit the method, the variables are destroyed. If method A calls up method B calls method C, then what you have is sort of a chain of stack variables and memory cells that are bound to those variables. And they'll stay around as long as those methods are still active. And when the methods complete and return, those variables will be removed from the stack. So that is stack dynamic variables. Now, I guess maybe I'll add one more little point here, which is something that I just taken out of something that I just said, which is that they are so typically encountered during method. So I want to say variables encountered during method execution. Variable declarations, we'll say. Variable declarations encountered during method execution trigger memory cell binding. And then exit from method. Actually, I want to say exit because exit implies you might leave the method but possibly return. I don't know. Return to it. So return from method triggers memory cell unbinding. Okay. So there are some advantages and disadvantages to this approach. So the advantages, one great advantage is support for recursion. We're going to have a very difficult time getting a programming language that supports static memory cell binding only to support recursion. And that's because a key element of recursion is that a method calls itself, and the previous version of, so if method A calls itself, when method A is called the second time, the previous invocation of method A still needs to remember something about its state. We don't want to lose that state. All right, so if method A calls A, calls A, calls A, and then triggers a base case, each one of these A's knows something about its local variables, and we don't want to lose the local variable information in this A when we call this A. And that is possible with stack dynamic variables because the stack dynamic variables that are located in this A are bound to a certain set of memory cells, and they will not be unbound until this A returns. So if this A calls this A, those original local variables and their values are going to be maintained in this A, and a new set of the same local variable names but with different memory cell bindings are going to be set up on the stack for this A, and then this A, and then this A. And so at this point, before we hit the base case, we actually have 4 sets of local variables, all with the same name but bound to different memory locations. So being able to maintain all that state is critical to the support for recursion. You don't have that with statically bound variables, right? If you had a language that can only support statically bound addresses for variables, then you would never be able to support recursion. Okay. Another advantage is it's possible to have memory recycling. You can't have that with statically bound address binding. So in this case, if you're in a method, it allocates a large array. When you exit the method, the large array is cleaned up, right? And another thing that's really nice about this approach is you have implicit memory management. That's kind of nice. You're going to see what happens when you have to do explicit memory management in a little bit. But this basically means that depending on the language, if you have, it's possible to have even complex data structures allocated on the stack. That doesn't happen with Java, but it does happen with C and C++. You can actually go into a method, have local variables that are complex data types allocated on the stack. When you exit the method, they're removed from the stack, and you didn't have to do any work to do that. It just happened automatically. So that's kind of nice. The disadvantage is lack of long-term state. And what I mean by that is if the only thing you had in your system was stack dynamic variables, and you exited a particular function, there might be no way for you to remember that you'd ever been in that particular function. And that could be a problem. I'm sure you've often encountered situations where you needed to remember that you did something once. All right? I often call those variable, I would usually have that memory in something like a variable that I call first time variable, or yeah, like a first time variable. And so remembering that you did it once, that you went in and entered a method once and then exited, and the next time you go in the method, if you've already entered it once, you're going to do a different set of code. Maybe there's some initialization code that you don't need to do. A good example for why you might want to use that would be something like connection to a database. So the first time you connect to a database, you want to remember that you did that, so that the next time you connect to the database, maybe you just get the database handle instead of going through the whole connection process again. And so having that memory ability to remember that is really important, and you may not be able to do that if you're using a language that just uses stack dynamic variables, because as soon as you exit a method, you forget that everything about the local variables associated with that method are forgotten. All right. So another disadvantage is overhead for memory management. If you don't have the option of using the static variable, you may run into situations where you really do need some ginormous array. You have to do a bunch of computations, you leave, and then you have to come back and do some more computations, and you just need the space for that array. It's like a giant scratch pad. And there's a lot of overhead associated with creating the array, so you just want to create the array once. But if all you have is stack dynamic variables, you may run into a situation where the methods that need to operate on the array have to keep recreating the array. And when they exit, they deallocate the array. And then you go right back into the method and reallocate the array over and over again. So here's an example of something like that that could be annoying. So I do something like this. So Java has a workaround for this. So I'm going to use C or C++ to give you an example. So there's a method that returns nothing. It's a void method. And I say void int array 5,000. Or let's make it 50,000. Okay. And you do some stuff with the array. And then you exit. But the thing is, you've got some loop that calls f, 100,000 times. So clearly, it really doesn't make a lot of sense to be allocating the array inside f. And you might say, wait, I can think of workarounds for this. Maybe what if you passed the array in as a reference? And I'd say, yeah, you're right. Some languages will let you do that. But I'm just illustrating the point that it's possible if the only type of memory management you have is stack dynamic memory management, that things can get kind of messy when you need to deal with large data structures. All right. I think that's a good place to stop. So